Alright, when last we met, we discussed metals that can have only one possible charge, mainly those metals in group 1A, 2A, and that friendly staircase step. But now we want to examine the dark, scary world out there of metals that can have more than one possible charge, mainly our transition metals. It turns out that iron is one such nefarious metal. Get it? Nefarious? Iron? Nefarious? Oh, come on. You thought that was funny. You want to laugh. I can see it. I know you want to laugh. You're just trying to resist. Go ahead. Give in. Embrace the geekness. Alright. Turns out that iron, being such a nefarious metal, can have a charge of either 3+ or 2+. How is it possible? Well, it turns out that atoms are kind of like people. The dictates of the octet rule only mandate that an element have its outermost valence shell, outermost S&P, completely filled. If we look at the electron configuration of iron, the electron configuration of iron is argon, 4s2. Matter of fact, to make this demonstration very effective, which I need to, let's actually take a look here and draw an orbital diagram. 1, 4s, 1, 2, 3, 4, 5, 3d. And if we count over irons 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 electrons into that 3d. So that's the electron configuration of neutral iron. Now, to obey the octet rule, all iron has to do is get its outermost S&P completely filled. The easiest way for iron to do that, remember that octet rule doesn't say anything about the D's, so all iron has to do to obey the octet rule is get rid of those 4s electrons, and then it will have the same valence S&P as argon. So that's exactly what some iron atoms do. They're going to do the minimum required out of them in life, and they're going to lose those 2 4s electrons. And when it does that, it forms an iron plus 2 ion, and it obeys the octet rule. It meets the minimum requirements in life. Now, some atoms are like Elmer J. Fudd. It turns out that half-filled D subshells and completely filled D subshells are highly energetically favorable. So, if we look at iron here, iron is really close to having a half-filled D subshell. It has 6 electrons into 3d, so it only needs to get rid of 1 in order to have a half-filled D subshell. So some atoms of iron, will lose the 2 4s electrons so that it obeys the octet rule, and then they'll go the extra mile, and they'll kick out one of their 3d electrons so that it has a half-filled D subshell. And if it loses 3 electrons, then obviously it's going to have a +3 charge, and its electron configuration would be argon, 1, 2, 3, 4, 5. Would be argon 3D. So iron can actually develop ions of two possible charges, and does so. 2 plus and 3 plus. Another example of an element that does this is copper. Let's take a look at the electron configuration of copper. Copper has an electron configuration of argon 4s, 2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. 3d9. Now, to obey the octet rule, all copper has to do is, like iron, get rid of those 4s electrons. And that may be what it decides to do. Some copper atoms will do exactly that. They'll lose 2 electrons, develop a +2 charge, and an electron configuration of argon 3d9. Now, other copper atoms are a little bit smarter. They're saying, now wait a second. A half-filled D subshell and a completely filled D subshell are pretty stable. So rather than getting rid of both of those 4s electrons, what if instead I take one of my 4s electrons, I move it to the 3D, and I kick the other one to the curve. In other words, I'm going to get rid of one electron to give myself a +1 charge. I'm going to demote another electron so that my 4s is empty, but now my 3D is filled. And just like with iron, you'll see copper atoms doing both when they form ions. You'll see some copper ions forming as copper +1, and you'll see some forming as copper +2. Lots of different transition elements do this. Some other quick examples that I won't bother to go into the electron configuration of, but another common one that likes to do this is chromium can do +2 or +3. You'll find vanadium +2, +3 as well. You'll find other examples. Tin. Tin does +2 or +4. You'll find lead doing +2, and you'll also find lead doing +4. So you'll find several different elements capable of forming multiple charges. Because of that, we have to have different ways of naming these compounds, not naming these ions. Write down Donna, D-O-N-N-A. Write down Donna, D-O-N-N-A. After you've done that, let's take a look at some rules for naming we're going to name ions capable of having more than one charge. Now, you're going to find a variety of opinions over what metals fall into this category. There is actually an international organization, IPAC, that settles this once and for all. However, if you go over the internet or look at one textbook and compare it to another textbook, you'll see what appears to be a high degree of inconsistency. So for my students, the rule we're going to follow is that if the metal is not in group 1A, and it's not in group 2A, and it's not aluminum plus 3, zinc plus 2, our staircase step, cadmium plus 2, or silver plus 1, then we're going to assume that the metal can have more than one charge and falls into this category right here. So this category consists of any metal ion that's not in group 1A, 2A, or along our staircase step here. To name these metals, you follow a couple really easy rules. You're going to write the name of the metal. Then you're going to write the charge of the metal in parentheses using Roman numerals. Then you're going to write the word ion. For example, I have iron, so I write iron. Then I write the charge on iron in parentheses. I have a 2 positive charge there, so I'm going to write 2 in Roman numerals and the word ion. I would pronounce it the iron 2 ion. For this iron right here, I would write iron, the charge on the metal in parentheses, ion. I'm going to type it too to emphasize something here. It's going to be difficult for me, and it's not going to let me no, lowercase. There we go. Alright, I've typed it there for you. And I've typed it for a special reason, because you need to know how to type it, particularly if you're using an online homework program. As we blow up the word iron 3 ion, notice, is there a space between the N and the first parentheses? No. This is all one big word smooshed together. There is a space, however, between the last parentheses and whatever comes after it. So there's a space here, but no space there. Also, notice, did I capitalize it? No, I went to great lengths to keep it lowercase. There are lots and lots of iron 3 ions out there, so it's a common noun, unless of course you're naming your kid iron 3, in which case kudos to you. Let's take a look at another couple quick examples just to make sure this horse is completely and utterly dead. If we wanted to, we could name these 2 friendly ions. We have tin. So we write the word tin, open parentheses, we have a charge of +2, so tin 2 ion. I have 4+, so I have tin tin-4 ion. Remember, for Roman numerals, when you're subtracting, you put that 1 first. So tin-4 ion. And that's how you name those ions of multiple charges, or of metals that can have multiple charges. Still, pretty easy, right? Chemistry is easy, life is hard. You know, I really like metals that can have ions with more than one charge. Matter of fact, I think they're so nice that some of the chemists and I named them twice. That's right. There's actually an alternative naming system for these ions that can have more than one charge. These non-systematic names are referred to as old-fashioned or Greek names. For example, if we look at our friend iron 2 and iron 3 here, iron 2 ion is the systematic name. Iron 3's systematic name is iron 3. There exists an old-fashioned nomenclature system that is unfortunately kept alive mainly by the health sciences that uses a Greek or Latin nomenclature system. The old-fashioned name for iron 2 is ferrous. The old-fashioned name for iron 3 is ferric. The only way you can know this is to memorize it. What you see is a chart of old-fashioned names for metal ions. You are responsible for knowing all of these old-fashioned names. That means you have to use the M word. I'm sorry, there's no other way to do it. You have to know that iron 3 ion is called ferric. Iron 2 ion is also called ferrous. Tin-4, stannic. Tin-2, stannous. May they win the Game of Thrones. Ooh, spoilers. Ooh, write down river. You got to write down rivers. I said spoiler, so write down river. R-I-V-E-R. Write down river. Spoilers, write down river. You have to know that copper 2 can be called cupric and copper 1 cuprous, and that mercury 2 can be called mercuric. Where's mercury 1? Or where's another form of mercury? We'll get to that in a little bit. The only thing I can really do to help you with this old-fashioned nomenclature is to point out that there is a pattern. That the higher charge has the smaller name. In other words, out of a pairing, ick always goes with a higher charge. If you have a small charge, you overcompensate by giving yourself a longer sounding name. OUS, right? Always goes with the smaller charge. Iron can be 2 or 3. 2 is smaller, so it's ferrous. 3 is higher, so it's ick. 4 or 2. 4 is higher, so it's the ick. 2 is lower, so it's the us. 2 and 1. 2 is higher, so it's the ick. 1 smaller, so it's the us. 2 is higher, so it's the ick. Mercury is a special case scenario. Mercury likes to bond with itself. And 2 mercury atoms will get together and form a unit, and together that unit will have a +2 charge. That means that each mercury within that unit has a +1 charge. So they'll say it's the mercury 1 ion. However, it only exists in this form. You never ever see this by itself in nature. They have to team up. 2 mercury atoms have to get together and stabilize each other if they're each to have a charge of +1. Therefore, I like to think of mercury 1 as being a polyatomic ion with a charge of +2. This polyatomic ion of Hg2+ is also referred to as the mercure Forgive me, I became a chemist so I didn't have to spell. The mercurous ion. All right, here's a quick quiz yourself. Pause the video, try these on your own, and then check and see if you got them right with me. Please tell me you paused. I know you paused. You had to have paused. If you didn't pause, I'm glaring at you angrily right now. All right. Let's take a look at the first one. We have the element strontium with a +2 showing. Strontium is a metal in group 2A, so its only possible charge is +2 when it forms an ion. So we simply name this the strontium ion. Then we see F2 parentheses G. Fluorine is one of our diatomic gases. So that's simply fluorine. When a chemist says fluorine, that's what they're talking about. I would also count it correct if you put fluorine gas. But it's fluorine. Then we see CS. Do we see a charge showing? No. So it's just cesium, and you can see that on your periodic chart in group 1A. Now we have Li with a +1 showing. So we have lithium, and lithium's in group 1A, so it can only form one cation. So we would simply call it the lithium ion. Now we see tin with a 4+ showing. Tin is not in group 1A, it's not in group 2A, and it's not one of those staircase step elements we memorized. Therefore, we would name it tin for ion. Because tin can have more than one charge, we have to name it with a 4. How do we know tin can have more than one charge? Because it's not in group 1A, 2A, or one of those staircase step elements we memorized. Last but not least, we see S with a 2- showing. So we have an anion, and when we have an anion made from one element, we add the suffix IDE to the name of the element. So sulfur becomes the sulfide ion. Chemistry is easy, life is hard, yes? One last thing, and that's polyatomic ions. Polyatomic ions are a group of atoms that together have a charge. Or another way to think of it as is a covalent compound with a charge, or a group of atoms covalently bonded together that have an extra electron or a shortened electron. This table here, and the table that you'll see in a few minutes, and if you're in my class I provided you a handout of this table, are a list of polyatomic ions, their name, and their chemical formula. You are responsible for memorizing all the polyatomic ions on this chart and the next chart. By memorizing, I mean you need to know the name, the formula, and the charge for that formula. Let's take a look at chromate. Chromate is CrO4 2-. What that means is that when we have that chromium atom bonded together with 4 oxygen atoms and 2 extra electrons, they have a charge of 2-. Common misperception is people want to think that each of those oxygen atoms has a 2- charge. That's not the case. That 2- charge belongs to that entire group of atoms. That entire group of atoms together shares those 2 extra electrons. The same for dichromate. If we're to look at cyanide down here, it's that carbon and that nitrogen together have 1 extra electron and a charge of -1. If I were you, I would make flashcards. On one side I would put the name, on the other side I would put the charge and the formula for the polyatomic ion. You are responsible for knowing all these. Your homework questions will start to drop these polyatomic ions into the questions and expect you to know the formula. If you have me in the face-to-face class, I give you a test over these polyatomic ions. Let's see, a couple to point out is, let's see, on this table, there are only 2 polyatomic cations you're responsible for. You have ammonia, NH4+, and you have mercurous, also called mercury 1, which is a polyatomic ion made from 2 atoms of mercury. So that's mercurous, mercury 1, Hg2+, and ammonia is NH4+. Do not confuse ammonia with do not confuse ammonium with ammonia. Ammonia is a named compound like water. NH3, no charge. NH4+, ammonium, NH3 with no charge is ammonia. So be aware of both of those. You're responsible for knowing both of those, by the way. Let's see, we have cyanide, Cn negative. Then we have thiocyanide. Thio is a prefix in chemistry, often used to denote the presence of sulfur. So in the future, whenever you see thio, you can think, I wonder if sulfur is present. Acetate is awesome. Acetate, C2H3O2 negative, can be written 2 different ways. You can write it like this, or you can write it like this. Notice the formula is the same both ways. In this formula, they split the 2 carbons and write them separately. But either way, it's acetate if it has 2 carbons, 3 hydrogens, and 2 oxygens with a -1 charge. This way provides some structural information, and that's the reason you'll see people write it this way. Then you have oxalate, C2O42 negative. Then you've got hydroxide. These ones you have to do by rote memorization. However, if we look at this next chart, we see another group of polyatomic ions, and these polyatomic ions contain some OXXO anions. I want to focus real quickly on these polyatomic ions. These polyatomic ions, perchlorate, chlorate, chlorite, and hypochlorite, are what are known as OXXO anions. OXXO anions are polyatomic ions containing oxygen. There is actually a systemized method of naming OXXO anions. In this systematic nomenclature, the 1 form of the polyatomic ion is declared the 8 form. For example, ClO3 negative is I know, random time jump, everything changed on you in the blink of an eye, but we declare 1 form, the 8 form. For example, chlor8 is ClO3 negative. If we write a combination of chlorine and oxygen that has 1 less oxygen, so we call our base form the 8 form, and then if we take away an oxygen, in other words, have 1 less oxygen, we refer to that form of the polyatomic ion the ite form. So one less oxygen than chlorate would be ClO2 negative. So we change the prefix from ate to ite. So that would be the chlorite form. And if you've had Latin, you know ite means is associated with less. So we've got ite. If we take away another oxygen, in other words, the base form minus 2 oxygens, we add the prefix hypo to the ite form. So we'd have hypo, and then we'd have ite. We'd have a prefix and a suffix. So when we subtract 2 oxygens from our ate form to make our polyatomic ion ClO negative, we would refer to this as hypochlorite. But we're not all about subtraction here. We can do some additions. If we add an oxygen to the base form, our base form plus 1 oxygen, we keep the suffix ate, but we add the prefix per. So if we added an oxygen to our ate form and made it ClO4 negative, we would refer to that as perchlorate. So we have base form is ate, 1 more oxygen is perate, 1 less oxygen is ite, 2 less oxygens is hypoite. Now, on your memorization sheet, you'll notice that you have all 4 of those polyatomic ions. If you can memorize them for chlorine, then you also know them for bromine and iodine as well, because bromine and iodine are in the same group as chlorine, and they can do any bonding that chlorine can. So I could ask you, and I expect you to know, the name of that polyatomic ion, even if it's not on your sheet. If bromine and chlorine are similar, ClO3 negative is chlorate, so BrO3 negative would be bromate. Iodine's in the same group as chlorine. So if ClO negative is hypochlorite, IO negative would be hypoiodite. So you're responsible for knowing all the halogen OXXO anions that you can make similar to that chlorine family. We also see that 8-ite pattern in more than just those guys. A couple others that we see it in. You have nitrate, 1 less oxygen. You change 8 to ite, so that would be nitrite. We have SO4 2 negative is sulfate, take away an oxygen, and you have 8 becomes ite, so you have sulfite. Just to beat the horse into the ground, you've memorized, or are going to memorize, that this is phosphate, so 1 less oxygen would be phosphite. So that can help you with your OXXO anions. And be aware of that naming convention. I've got a table for you. Here's a table of OXXO anions that you're responsible for. Let's see, what have we not covered when it comes to anions? Aha! We've covered our chlorines. We covered the nitrites, nitrates. let's take a look at our phosphates, and these same rules for phosphates would apply for phosphite. If you add a hydrogen nucleus to phosphate, you're adding one hydrogen, so you'd say monohydrogen phosphate, and the charge goes to 2 negative. If you add 2 hydrogens, it's dihydrogen phosphate, and the charge goes to -1. And we could have monohydrogen phosphite, and we could have dihydrogen phosphite as well. Then if we look at carbonate, you'll see that we have HCO3 negative. Hydrogen carbonate can be named 2 ways. It can be called hydrogen carbonate, or it can be called bicarbonate. In chemistry, bi does not mean 2, it actually means the presence of a hydrogen ion. So when you add that hydrogen ion to carbonate, you not only have a hydrogen present, but notice you've changed the charge from -2 to -1. We can use that bi principle not just with carbonate, but we can also see it with our sulfate and our sulfite. For example, we could have hydrogen sulfate or bisulfate. We could have hydrogen sulfite or bisulfite. So be aware of that prefix bi and 2 different ways to name that compound. If you were face-to-face with me, I would show you that compound and ask you, I would show you that polyatomic ion and ask you to name it for me twice. Give me both names. Thiosulfate, permanganate. Permanganate's one I love. I used it in my research, so I'm kind of stuck on it. That's it really for this lecture. Beep.